Okay, we are on page 82. 82. We're just going to go right into the exercises because they're just blank. Are you guys sure you don't know how to do this? Like, if you look at this question, could you calculate it? Give it a go. Number 2 on page 82. I think you can do it. The question is down on your page. You don't have to read it up here. The text is probably too small to read up here. You can read it on your page. Why are you looking at what I'm doing? Write your own reaction. You guys know how to write this reaction. We're doing number 2 on page 82 because I don't believe you guys that you don't know how to do titration calculations. I think you do. If nothing else, you can write yourself a balanced equation. Start with that. Can't do any sort of titration without a balanced equation. Call me over if you get stuck. I did it all in one line, but you don't have to. Okay, you can do it in steps. You can be like, oh, I'm going to find the moles of H2SO4. Yeah, so you might just do this step here. And you could, of course, not do it in milli. You could do it in liters. That would totally be good. Yes? I could not hear that. When what? Lead, when it dissociates, is 2+. Like PbCl2?
Oh, not lead. Sorry, mercury.
Oh, mercury stays together because it's a polyatomic cation. It's weird. Mercury 1 anyway. Yeah. So any stoichiometry problem, any titration problem is really just a stoichiometry problem. So in the middle, you are always going to have, you're going to find moles of A and you're going to convert it to moles of B by using the balanced equation. So it's merely a matter of saying, what do I know all this stuff about? Oh, I know everything about the sulfuric acid. So I can find moles of sulfuric acid. What do I not know something about? Oh, well, that's my unknown. There it is, my KOH. So I'm going to convert from moles of H2SO4 to moles of KOH. And then finally, if I'm asked to find the concentration, that's going to be my moles over my liters. If you want to do it all in one line, you can by sticking a 1 and then dividing by your liters, or you can do it in a separate step. Is good? Questions? Okay, that's going to take us on then to solubility titrations. And this is on page 85. Okay. Because this has like a little animation to go with it, kind of.
Titrations can be used to determine the concentration of a specific ion in a sample solution. Here we'll see how titrations involving precipitation reactions work. Here is a setup for a titration of a solution with an unknown concentration of Cl- or chloride ions. This long tube is called a burette. Burette can also be spelled B-U-R-E-T-T-E. This valve, called the stopcock, is closed to keep the liquid in the burette.
Okay, so we have the burette, we have the stopcock, which is also the word for the valve.
When it's opened, liquid will drip or flow out of the bottom of the burette. In this example, the burette is filled with 0.100 molar silver nitrate solution. The solution in the burette is called the standard solution.
What is a standard solution? See if you can dredge that out of your memory from last year. Yes. It is one where we know the concentration. Standard just means known, okay?
The standard solution has a known concentration. In this case, it's 0.100 molar AgNO3. The standard solution can also be called the titrant.
Excuse this interruption. Good morning, Burnaby Mountain. Here are the names for the winners of the Phone Free Friday raffle draw.
The names are Sierra Barnacote, David Kovari, Alicia Leon, Mario Lodano.
We'll be coming by your classes to drop off your $25 Low-Heat gift cards. We look forward to having everyone participate for future Phone Free Fridays. Thank you.
Nice.
In this titration, a solution containing chloride ions is added to an Erlenmeyer flask and placed under the burette. The solution in the flask is called the sample.
Okay, so the solution in the flask is called the sample, and it has an unknown concentration. Does anyone remember what it's called? It's not the titrant, it is it's the thing you're analyzing, it's the analyte.
It's the solution with the unknown concentration. It can also be called the analyte.
Okay, and the reason it's called the analyte is because you are analyzing it.
Because this solution is being analyzed to find out the concentration of chloride ions in it. In this titration, a few drops of sodium chromate solution are added to the solution.
Why are we using sodium chromate? It's an indicator. Because if you just start dripping silver into chloride, you're going to start getting a white precipitate. Now, how are you going to, and then it will dissolve, and eventually you'll get enough concentration of silver that you'll hit KSP, and then you'll actually start to form a precipitate. So you'll drip it in, and it'll dissolve, and you'll drip it in, you'll get some precipitate, but it'll redissolve. And eventually, you'll get like a little tiny bit of, or is that right? Nope, never mind what I just said. Let's just keep going. Have I pressed record? I have, excellent. So my screw up is here for posterity for anyone who wants to watch this through the years. Great.
The sodium chromate solution is known as an indicator in this titration. It will change color at what is called the end point of the titration.
Do you remember what the end point of the titration is? The end point is when the indicator changes color. Literally, that's what it is. Okay, the end point should correspond to there's another E point. Anyone remember what it's called? An equivalence point.
We'll show you how all of this works. We'll focus on the solutions. We'll dissociate AgNO3 into its individual ions, which are Ag plus and NO3 minus ions.
NO3 minus, of course, is a spectator. So what can we do with it? Ignore it. Yes?
The nitrate ion does not form any precipitates. It's a spectator ion here, so we'll just delete it from our discussion and tidy up a bit. So you can think of the solution in the burette as a source of Ag+, or silver ions. In a titration, we briefly open the stopcock. The solution in the burette drips into the flask, bringing Ag+ ions with it.
What will Ag do with Cl? Form a precipitate.
Let's take a closer look at what happens in the flask as silver ions are added to it. Now we've zoomed into the flask. Silver ions preferentially bond to chloride ions rather than chromate ions.
Did you guys catch that? Who does silver like bonding to best, chloride or chromate? Chloride. This is important because silver will not react with chromate until all the chloride is gone. And that's what we want. We want something to say, oh, all the chloride is gone.
This forms the precipitate silver chloride. Because silver chloride is white, the solution turns to a milky yellow color.
It's yellow because the chromate ion, when it's dissolved, is yellow, okay?
As silver ions are added, some will temporarily bond to the chromate ions. This will form the precipitate Ag2CrO4, or silver chromate. Silver chromate is reddish-brown, so the solution will turn a slightly reddish color.
But what will happen next? Bam! Because the silver does not like being with chromate as much as with chloride, it will dissociate and it will grab onto the chloride instead.
But silver preferentially bonds with chloride, so as the flask is shaken, the silver ions will leave the chromate ion and bond with available chloride ions, and the reddish color will go away. The solution will turn red momentarily as more silver is added, but as long as chloride is still present, shaking the flask will make the red color disappear. Added silver ions will continue to bond with the remaining chloride ions. At a certain point, all of the available chloride ions have bonded with the silver ions.
Now, if we did not have an indicator in here, would there be any way of knowing that our cloudy white solution was finished reacting? No, you'd be like, it's cloudy white. It gets a little more cloudy, but how do you know when it's at its most cloudy? Like there's no way of telling, okay? That's why we have our indicator. Uh-oh.
Since there are no chloride ions left, any silver ions that are added will have to bond to the chromate ions. The formation of silver chromate precipitate will cause the solution to turn red again. At this point, when the flask is shaken, the red color will no longer disappear. There are no chloride ions available, so the silver will have to remain bonded with the chromate. We say the solution has turned a slight permanent reddish color. This is what's called the end point of the titration. A permanent color change of the indicator signals the end point of a titration.
So we have the end point, which starts with an E. We have the equivalence point, which also starts with an E. People sometimes mix them up because they both start with E. However, equivalence point kind of has the word equal in it. Yes? So equivalence point is when the moles are equal. Yes? or at least when they satisfy the stoichiometry. This is one-to-one stoichiometry, so they will be equal. And the end point is just when you should end the titration. Not equivalence. Equivalence. There's no L after the QUI. Equivalence, not equivalence.
The equivalence point, or stoichiometric point, of this titration is the point where the moles of Ag plus added to the flask is equal to the moles of Cl minus that were in the original solution in the flask. In most titrations, if the proper indicator is used and the technique is good, the equivalence point and the end point are very close, and they can be assumed to be the same point.
So this will become important when we're doing acid-base titration, because if you choose the wrong indicator, it will change color somewhere else other than at the equivalence point. For this one, it doesn't matter.
Once we reach the end point, we must stop adding silver ions to the beaker. This is because we want to know exactly what volume of 0.1 molar AgNO3 solution was needed to just react with all of the chloride ions that were in the sample.
Whoops, go back. One of the most common mistakes that people make is they calculate the moles of chloride, right? And then they say, oh, I must divide by this combined volume of the titrate and the analyte. What's wrong with using this volume to calculate the concentration of chloride? Discuss that with your partner. Why would we not use this combined volume when we're taking moles and dividing by liters for concentration of chloride? Are we still thinking, or are we done? Okay, why do we not use the total volume? Elliot. Yeah, we're calculating the initial concentration of chloride. We want to know how much chloride there was in the sample, not how much there is in the sample plus the titrant, right? How much, actually, what is the chloride concentration right now in this volume? 0. So you can see it's kind of like it's irrelevant, yeah?
Solution was needed to just react with all of the chloride ions that were in the sample. We record the initial reading of the AgNO3 solution in the burette, just before we start the titration. Then we begin the titration, adding drops very slowly while swirling the flask. As soon as the endpoint is reached, we close the stop clock, stop the titration, and record the final burette reading of the AgNO3 solution.
Question, is it helpful to fill this in, or would it be more helpful to just have it printed out without the filling in bit?
I don't know, honestly, if it was just printed out, I don't really care about it.
That's what I felt. That was why I left blanks. Okay, fair.
The difference between the final burette reading and the initial burette reading will tell us the volume of AgNO3 solution required to reach the end point of this titration. And this volume will be needed for the calculations used to find the concentration of the chloride ion in the original sample solution.
Oh, and I guess that's it. Try the practice problem. See if you remember how to do this. And I want to see correct sig figs. Oh. Because AP, if they're asking you to do this, will want to see correct sig figs. Oh. Is our first number 10 point something or 9 point something? 9 point something. Good. We're all reading down. Excellent. Why does what end up bigger at the bottom? The number at the top is 0. The number at the bottom is 50. That allows us for our final volume to be larger than our initial volume, so we can subtract final minus initial and get a positive number. Yes? So we're starting with 9 point let's see, that's 987.6 something. 9.6? 9.6 what? 2, sure. 1, sure. Is that good? No, what have I forgotten? Units. Milliliters. I'm going to make it 24.12 to make my math easier. It could be, or it could be 24.15. Actually, that wouldn't be bad either. Are we good? Excellent. Yep. So basically, write a balanced precipitation equation. Net ionic is usually used in precipitation titrations. Write what you want to find. You should have a map of your calculus. No, you don't need a map, but you should go from moles of A to moles of B. And then finish up. Ooh, here's a special one. Question number 5. What do you notice about question number 5? There are multiple trials. What do you do when there are multiple trials? You find the average of them. Now, does anyone have any thoughts about our data there? Trial 1 is an outlier. Okay, so you would leave out. So leave it out of your calculations. How did these questions go over the weekend? I mean, I don't expect that necessarily you did all. How many people did all of them? Thank you. They were good? Any questions on any of these? You can ask me later, sure. Okay. So now we have covered all the various types of situations. Now we say, oh my goodness, you have how many types of solubility math problems? 1, 2, 3, 4, 5. And you need to use the right tools in the right places. So let's just quickly go to page 92. Woo! Page 92. This what do you call it? 3.3H is really just about being able to spot the problem. Okay, to be able to recognize what the problem type is. So for almost all of these, you're going to write the C, you're going to write the KSP, you'll have to find ion concentrations, and you'll plug things in and you'll solve, okay? Let's read this and see if we can figure out that this is given the solubility, find the KSP. Given the solubility, find the KSP. A small piece of the mineral smithsonite, ZnCO3, has a mass of with a mass of 0.00014 grams, just barely dissolves in 100 milliliters. Calculate the KSP. Would you know what to do with that question? I got 1 nod, 2 nods. You don't have to squint at it, it's on your paper. Example number 1. You might need to calculate the KSP. How would you do that? So you would do grams per milliliter into molarity, moles per liter. Yes? And then what? This would be your solubility. Do you have 2 compounds or 1 compound? 1 compound. So what is your ion ratio going to be? Will it be stoichiometric ratio?
Yes.
Yes. So you just off you go. Yes? So KSP is equal to S squared. You'd have to show like the whole C and the KSP expression and all of that, but that's how, there you go. All right, a saturated solution of BAF2 contains 3.58 times 10 to the minus 3 moles of BAF2 in 1 liter of solution. What is the KSP? Could you solve this problem? Yeah? You would take your moles and you would divide by your liters. That would be your solubility. What would our KSP equal here? KSP would equal 4x cubed. So if this were a multiple choice, you could just go straight to that. Can you do that in the written response? No, you have to show the C and the KSP expression and then show shoving those things in and you're all good. Okay. The solubility of MgOH2 is found to be 1.2 times 10 to the minus 3. What is its KSP? My gosh, it got even easier. Yes? It's just the same thing over and over and over again. This one we already have the moles per liter. And then KSP, because it's an MgOH2, it would be equal to 4x cubed. Now, I will let you know that the examples on this worksheet were not meant to be assigned. They were meant to show you the type of problem, okay? However, over the years, I've had many students be like, where's the answer key? And so I made an answer key if you're interested, but these are not supposed to be assigned questions, all right? But if you're like, I must have more questions, here you go, all right? Ooh, type 2, given the KSP, find the solubility. Don't just look up KSP. This is where people get excited and they're like, oh, I was given KSP. I look up KSP and then that's one of the multiple choice answers. Ha 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 ha. And I'm supposed to find solubility and I write the KSP as my value. Oh. So we have 1 compound. For this one, if you're doing a written response, you need to write a let statement. Let X be the molar solubility of AB, whatever it is. Write the C, write the X's, write the KSP, plug in the KSP and X's, use algebra to solve for X. For multiple choice, just use KSP equals x squared or KSP equals 4x cubed. Can you tell? Would you know how to do example 4? What would you do for example 4? You would look up the KSP. You would write the C. You'd write the KSP expression. You would use the let statement. Let X be what? Solubility of PbSO4 in molar. And then you would do all the stuff. Yes. And you would end up with a KSP equal to x squared. You would solve for it. Whoa, that does not look like an x. What would you have to do once you found the molarity? Molarity goes to, moles goes to grams. Is good? Next question, calculate the molar solubility of Ag2CrO4. You would look up the KSP. You would write the C. You would write the KSP expression. You would write the let X be the solubility. Then you would do all the mathy stuff. And you would get the molarity. Is good? Yes? You know what? If it's not specified, I would always go with molar solubility. Yeah. If it's not specified, I would assume molar solubility. Yeah. Well, you can say, what's the solubility in grams per liter? Right? But you would say solubility in grams per liter. Molar solubility specifically is moles per liter. Ooh, could you recognize what to do for number, that should say number 6. Can you recognize what to do for number 6? Yes? Once you've got this, yes, then you can solve for X. Then you can solve for OH, which is 2X. Is good? Okay, so we've got solubility KSP, we've got KSP2 solubility. Type 3, maximum and minimum problems. Do you remember in maximum minimum problems, are they dump and stir or are they mix and match? Mix and match. So you will not expect the concentrations to be equal to one another. And in this one, because you're given 2 compounds, you will need to identify the precipitate. Of course, as always, write the C, write the KSP, plug in KSP in one ion, and then you'll just solve for the other ion. These ones are probably one of the easiest ones to do. Number 8, what is the maximum lead possible in a 0.1 molar NaCl solution? Who is the compound of interest here? Who are we interested in? Lead chloride, right? We're interested in the lead getting together with the chloride. What are we going to do with the sodium? Ignore it because it is a spectator. So you will be dealing with this equilibrium, PbCl2 in equilibrium with Pb2 plus 2Cl minus. And here's where people tend to go, they're like, oh, this is 0.10 molar, therefore this must be 0.05 molar. Are we happy with that? No. I hope you're not happy with that. Why is it not 0.05 molar? Because it's a mix and match. Anytime you have a maximum question or a minimum question, you have to assume that they are not equal to one another. Okay? You have to actually calculate get your KSP from the data booklet or from the question and then answer it. So this is not 0.05. No. Look up, plug in 0.1 molar, and then you'll solve for lead. This next one is nasty. Why is the next question particularly nasty? Number 9. Doesn't it sound like we've done dump and stir here? Right? They're trying to trick you into thinking you have dumped and stirred here, but there is no reason to assume that. Okay? You are given one ion concentration and asked for the other ion concentration. It has a KSP, therefore you have to go with using the KSP to solve. How would you recognize that number 10 is a maximum minimum problem? At the moment the precipitate starts to form. That tells you you're going to find the concentration of one ion, plug it in, plug in KSP, solve for the other ion. What about number 11? How can you tell it's a max-min problem? Look, maximum. Oh, or it can say without forming a precipitate. Either of those will work. Okay? Q, will a precipitate form? Again, you're going to identify the precipitate. You'll have to find the concentration of the ions because you're mixing two solutions. You will probably need to do a dilution calculation. Yes? You're going to write the solubility equilibrium equation, write the Q or the K trial. Actually, someone called it QSP. I kind of like that QSP. Yeah, that was cute. All right, and then you compare your Q to your KSP. If this is mixed with that, will a precipitate form? Oh, look, we have two concentrations. What will be observed to happen? What are they asking you there? What could happen if you have lead and bromide? You could get a precipitate, but they're assuming that you can make that leap to say, oh, I could have a precipitate, not just like, I don't know, what would I observe? And then, of course, we have titrations. This one, you're not going to write the C, you're going to write the precipitation equation. Do not write the C for a titration. It's the only one where you don't write a C. Okay? Titration. Titrated. Ooh. Pretty easy to recognize them, yes? And then finally, there's type 6. Given the ion concentrations, find the KSP. This should be pretty straightforward because, again, you've got one ion concentration, you have another ion concentration. What else would you do but, like, put them into the KSP expression? Does that make sense? Like, I mean, there's nothing else to do there. Okay. So why don't you try 1, 2, 3, 4, 5? Okay, 1, 2, 3, 4, 5. There's one of each kind. If you find you're good on those, you're probably ready for the quiz on Wednesday. And if you try those and you're good to go, then you don't have to do, oh look, 3.3i. So many soluble melody math problems. And look, 3.3j. So many more solubility math problems. You don't have to do any of them if you know what you're doing. Do you know what I mean? Yes? So go ahead and try those 5. Unless I have one here. Let's check. Look, I have one here.
I think they probably just asked us like size of the long but they still.
No.
Elvin's gonna be asking for a wide.
Yeah.
It's always class, bro.
So they're all very similar.
Yeah. All. Go do it. Yeah. I don't have fun today. Oh, wait, and then I found that it's fast because I didn't say I was gonna get from bronze. They don't have real
I'm also going to give you some AP solubility questions. Okay? I just have to figure out which ones they are here.
Friday, we went to Oh yeah. Oh, who's Brian? How much the five of the Brian? 5 minutes and outside 3. You're not gonna go there. War. Is that getting left? You know, we have left. You left. No, I know that. Bro. Got it.
Yo, you're not that smart, okay?
Infinite hating, like, bro.
You're the hater, bro.
You're a hater.
You're the girl that makes me for me.
That's right. And the only way to see the best part of all is it on here. I love you. He's got a disc job.
He's really.
He did a so random.
One, all the.
Yo, I'll do my friend in there. Oh my god. You say that with I mean, I think don't worry, he also said that under this time.
I like having your family because that makes me happy. I can understand that. This was never my happy place. So, we're done. Let's go.
No, like, I was listening about it.
I know
Did anybody not get the AP questions? Here's how it's gonna work. I have tons of review, regular review, multiple choice review, all kinds of review, but you don't get it until you've done this.
Oh, no.
So you show me that this is done, I will give you the other reviews.
Alright.
I'm holding them hostage until you're done this.
I think this is my prize for you to win this preparing for that, we lost balls. They work. No, I think what it is. I think we do. He went to work.
Did you not get one?
That's right.
And that's okay, don't worry.
Let's see you say things like I left at 11:30 to go home by 6:15. We're trying to make up there. Or make us cluster, or in a cluster. Yeah, it's sagging. You killed it. Looks exactly. Running the Saturday.
Jeremy,
Yeah.
you did the challenge.
What's that left there?
I don't know.
I have no idea. I have no idea.
Which one left? Why is it left? Oh, maybe that's possible. I don't know.
Be right there.
You can write it out. That's fine. If you.
It's recording, right?
But. Oh.
Yeah.
Probably do it first tomorrow, what do you think?
Yeah.
And then we can do your test on Thursday.
And then you Oh, so
Makes me unhappy. Well, okay, so I fixed it last week. I took everything apart. I packed everything inside. There was so much cursing and swearing. It was taking it apart, putting it back together. There were many things that did not want to go back where it was supposed to. And so much cursing and swearing, much least ever was wrong. But finally, it was done. I put the clothes in the dryer. It was wrong. I was then my son was
Oh my god! Wait, you didn't do that.
I didn't do this one. I did the late one, bro. I was sick. I had COVID. No, I'm. No, I
No, bro. No, bro, that's not me. That's me, dude.
Not just
That's
that.
not me. I actually have to. It's okay.
Brush spoons. Yeah, and so that's done. But you can't just like go get the parts.
Okay. This is how you do this exam, okay?
On a Saturday.
You look at question 7, and if you can solve it, you got a 5. If you can't solve it, it's 2.
So I just.
Yes! Yes! I'm hoping that I got one machine. I'm gonna say hi to my wife.
I don't want any drawing. I want to.
Yeah. Not for you guys to take us. Something academic. I have to use my, I have to use my brain.
Oh, yeah, sure.
No.
Bring it differently.
Don't worry, don't worry. I will be hitting up my boy. Mr. Madden. Why is that funny? That was pretty funny. What's so funny? I got like honestly, this is better. That's such a genius. Yeah, I know.
In the next one.
Oh, you? Oh, I didn't even start. I thought I was starting today. I'm gonna finish it. Yeah, no, but because you have your transcript, but the system is like top down like US schools.
Andrew,
Okay, so you be screwed. I'm sorry. Around the